Okay, so we're going to split the half hour. I'll speak for the first 15 minutes on the astrophysical motivation for doing what's the title of this talk, deriving column densities. And I'll also mention some basics of absorption line spectroscopy, some complications, and a procedure we call hyperfine deconvolution. And then the second half will be by Arshia Jacob, who is leading the analysis of SOFIA data for the HiGAL legacy program. And she'll describe a specific tool that is very useful for dealing with this problem. So absorption line spectroscopy is a very powerful tool for studying the interstellar medium, because we can study the composition of interstellar clouds by looking at background continuum sources that sort of act as a laboratory lamp, and then we can analyze the material in front of that lamp, which may lie in a series of spiral arms between us and the source. And because of the differential rotation of the galaxy, these spiral arms are shifted in velocity, and therefore, because of the Doppler shift frequency, making it possible to observe multiple different clouds along a given sight line. So there have been a couple of large absorption line surveys in the far infrared to look for molecules that are most easily observed in that spectral region. And these are essentially hydrides, molecules containing one heavy element atom and one or more hydrogen atoms, which, unlike the non-hydride molecules, have their fundamental rotational transitions in the far infrared rather than the radio. So I've listed a number of examples of hydrides here on this slide. There are also two very important fine structure lines, the 63 micron line of oxygen 1 and the 158 micron line of carbon 2. And these are also in the infrared. So there have been two large surveys. One was carried out with the HiFi heterodyne instrument on Herschel. It's called Prismus. It was led by Mary von Geran. And there's one underway that I'm co-leading with Peter Schilke with the Great Spectrometer on SOFIA, which provides similarly high resolution. Just to sort of motivate this a little bit, let me describe just one application of the kind of studies that have been done. And this involves some of the hydride molecular ions I had on the last slide, OH+, H2O+, and ARH+. AR is argon, and this is a thing, the argonium ion. And all three of these are produced by chemical reaction sequences in the interstellar gas that are initiated by cosmic rays. So this is a diagram from Arshia Jacob's 2022 paper that is currently under review, which shows how this happens. So a hydrogen atom can be ionized by a cosmic ray. It can then charge transfer with an oxygen atom to form O+. And then the O+ ion can react with H2 to form OH+, which we can observe with SOFIA. And then a second reaction gives H2O+, which is also detectable with SOFIA. And so the abundances of these two molecules basically increase, at least monotonically, although not in exact proportion to the rate of ionization by cosmic rays. And therefore, if we have a detailed model to understand this, we can infer the density of low energy cosmic rays, not just in the vicinity of Earth, but throughout the galaxy. So that's just one application, actually, of several. So let me now show some example results from HiGAL, again from Jacob et al. 2022. And so what you see here are the spectra we obtained in the left-hand panel for 7 different species that we could observe. And these are all carried out towards the source W3OH, which is emitting, in this shaded region near the center of the plot. But we're actually not very interested in the source itself. We're more interested in the absorption by the foreground material that is unassociated with the source. And that's what you see here. And basically, we go from spectra plots of intensity as a function of frequency represented as a velocity with respect to the local standard of rest. We go from that to column densities, which are shown on the right-hand panel. So the column densities are the integral of the volume density along the line of sight, and one has to compute them for a given velocity range. So really the units are centimeters to the -2 per kilometer per second. So the subject of this presentation then is, how do we go from what you see on the left to what you see on the right? Well, there's a few key ingredients. The first of these is the relationship between flux and optical depth. And because these are the bright continuum sources, we can neglect spontaneous radiative decay and just consider absorption and stimulated emission of the radiation field of the background source. So that simply gives us a flux that is equal to the continuum flux, which we'll call F0, times e to the minus tau, where tau is the optical depth. And then there's a relationship between the optical depth per unit velocity interval and the optical depth and the column density per unit velocity interval, which is shown by this second equation. So what's in here is the wavelength lambda, the spontaneous radiative decay rate, the Einstein A coefficient, and then the fraction of molecules in the lower and upper states of the transition. And one note here is that if you measure things on the right-hand side in CGS units, your unit will be centimeter to the -3 seconds, and that's 10 to the -5 centimeter to the -2 per kilometer per second, which is a more natural unit for dNdV. Obviously, we also need to understand the fraction of molecules in the lower and upper states. Although sometimes we have a very simple case where all the molecules are in the lower state, and we can neglect the second term in the denominator here, the negative term that corresponds to stimulated emission. Just one note on where one can find line wavelengths and spontaneous radiative rates. And so I've listed a few sources here. There's the JPL line list, the Cologne database, and then a sort of combined tool that accesses both of these for molecular transitions called Splatterlog, that is created by NRAO. And then for atomic transitions, one can find these data in a database maintained by NIST, the National Institute for Standards and Technology, and also an atomic line list maintained at the University of Kentucky. So these are very valuable for searching to determine the identification of unknown spectral features as well. But in addition to referencing these databases, it's always very good practice to cite the primary sources as well where possible, because there's a huge amount of effort obviously goes into determining these, either by laboratory measurements or theoretical calculations. So there are a few complications that come into play that I'll mention briefly, and which are dealt with in the X-class program that Arshia will describe in a minute. The first is that we often use double sideband receivers. That's true for hi-fi and for great, where there are basically contributions at any given measured frequency from an upper sideband and a lower sideband, both of which have the same frequency difference from the local oscillator. So there can be an ambiguity, or there is an ambiguity, as to whether a particular spectral feature is formed in one sideband or the other. In other words, what its true frequency is. That can be resolved by using more than one local oscillator setting if it's unclear. The other thing that can, the other effect though, is that you'll always see continuum from both sidebands. And so even if you have complete absorption in one sideband, the intensity you measure won't go down to zero. It'll only go down to 1/2 the continuum flux, assuming the sidebands have the same gain. And so there's a modified equation that I've written here for how one can determine e to the minus tau if the fluxes involved are double sideband fluxes or temperatures. At SOFIA, of course, we also have atmospheric absorption that was described in the case of X's by Curtis's presentation. And with great data in the pipeline product, what will have been done is that the atmospheric lines will have been removed with an atmospheric model, and separately the wet and dry contributions will be modeled. So the point here is that the water vapor content is much more variable than the other contributions to atmospheric absorption, so should be treated separately depending on the precipitable water vapor at the time of the observation. Another complication, as you saw from the slides, is that there may be emission lines in the source, and these one can try to remove by modeling the spectrum of the background source. And these may be emission lines of molecules other than the one that you're observing in absorption. And then the final complication is that many molecules we're interested in have hyperfine structure where there's a splitting due to the interaction between the nuclear spin of one of the atoms. In this case, it would be hydrogen in OH. So that leads to a splitting into multiple states of different total angular momentum. And in OH, there's also a lambda doubling that splits, in fact, a larger splitting into states of positive and negative parity, depending on how the angular momentum points along the nuclear axis, which way it points. So in reality, this 119 micron feature that is observed with SOFIA is split into 6 components. And this spectrum actually shows the effect of 3 components, which is represented by this set of bars that show the hyperfine splitting. And so one has to remove that effect, which has been done here. And you can see that there's a single absorption component, but that gives rise to multiple absorption features. You can see 2 of them, and then the third one gives rise to the wing here. So we have to disentangle this essentially by deconvolving the observed spectrum from the hyperfine structure. I had a homemade code to accomplish this, although it's also done in X-class, as Arshia will explain. You can take the column density dndv as a sum of n Gaussians, each with an adjustable height, width, and centroid that you're going to tweak for each one of these Gaussians. So you do that, you convolve the column density distribution with a hyperfine structure to get the optical depth. You take e to the minus tau, which then can be compared with the observed spectrum. And then you can use a chi-square minimization to vary the 3 n parameters, 3 for each Gaussian, to optimize the fit. So here's an example of where we did that. The top is a SOFIA spectrum of the HCl plus ion shown in the histogram. And the green curve is what you get after hyperfine deconvolution. And this is a good fit because you can see that after convolution, the red curve, it agrees well with the histogram representing the observed data. Same was done for H2Cl plus, a related molecule that was observed with Herschel, and the effect there is smaller because the hyperfine splitting is small. And you can see that when you've done this, these two spectra that look sort of nothing like each other basically look very similar with 3 strong features that coincide. So let me leave that there and now turn it over to Arshia.
Thank you, David. I'm about to share my screen. Can you see my screen?
Yes.
Okay, great. Right. So now I'll talk to you about a specific tool for line analysis called X-class. But before that, I'd like to re-emphasize or motivate you once again as to why we require such tools. So as David mentioned, the spectral signatures that we see that are observed from these different chemical species are unique probes for the different regions in which they arise. So modeling them is the first step for characterizing the nature of the regions from which they're observed or formed. So without further ado, X-class stands for the Extended CASA Line Analysis Software Suite. And as its name suggests, it runs within the CASA environment. And this toolbox was developed by the University of Cologne. Now, of course, X-class does run outside of CASA, which I'll get into in a minute. Now, the main aim of X-class is to automatically identify and fit astronomical spectra. It runs through a model optimizing interface known as MAGIX, and I would highly recommend reading or going through Thomas Muller and collaborators' papers which explain the workings of X-class. Now, you can also download X-class using this link, which would be useful for your tutorials. Now, going back to what I mentioned about running X-class outside of CASA, it is mainly done using Python subroutines. But at this point, it is very important to make sure that you have the right Python packages and libraries set up. And by this, I mean very specific versions of each Python package and library, the details of which you can find within the X-class manual under section 1.5. So moving on and assuming that you have downloaded and correctly installed X-class, we'll take a look at how you can run X-class without CASA and just through Python subroutines. So X-class basically models your observed spectrum by generating a synthetic spectrum, which is obtained by solving the radiative transfer equation, which is shown here. Now, this is shown for a single species, but summed over different components I. And it is done over an isothermal object in one dimension. It assumes conditions of local thermodynamic equilibrium, but newer versions of X-class can also include non-LTE effects. Now, it also takes into account optical depth effects as well as line blending, all of which require information about the spectroscopic parameters of the different species, such as the frequencies, as well as the Einstein coefficients, etc., which David had already mentioned in his slides. Now, X-class does this by accessing different spectroscopic catalogs, including CDMS, like David mentioned, through the WAD-MC portal. Now, what are the main files that X-class would need when you're running an X-class fit? Now, the main function that we're going to look at is called myXClassFit, of course. And the main input files are firstly the observed spectrum, which can be in any sort of ASCII or TeX format. And you will have to input the observed spectral line profile or the intensities as a function of frequency, because X-class does not have any information about the local velocity scales that you use in your spectra. And if it has to identify different components, be it disentangling the contaminants along the line of sight or the line that you're concerned with, it requires this frequency information. In addition, it also requires continuum data. So your spectra should be prior to baseline subtraction, which is very important for the absorption spectra that we're dealing with. The next thing that you require is the fitting algorithm in the form of an XML file. Now, the XML file is just a format file which decodes this information. And the main algorithm that is used by default is the Levenberg-Marquet. There are other algorithms included, including the nested sampling, genetic algorithm, Bayes algorithm, simulated annealing, and so on. Now, the differences between these algorithms are mainly in computing time and in how it optimizes its solution, whether it's done locally or globally. And for all of our purposes, the Levenberg-Marquet algorithm is perfect. Now, the other important file that we require is the MolFit file or the molecular data file. Now, this describes the parameters of each given molecule, and you can have multiple molecules and multiple components describing the different parameters for your line of sight. Now, the main input for this is the gas temperature, the column density, the line width, and the velocity offset, which represents the position. And all of these components are by default fit using different Gaussians. But if you would like to fit, let's say, for example, a void profile, you can also mention that under this specific keyword. Now, the keyword can also be set to non-LTE, but in this case, you would also have to mention the relevant collisional rate coefficients files as well as external radiation files. Now, the other thing X-class would require from your side is information as to whether this is a foreground component or a core component. Now, X-class differentiates between these things based on the source size as well, but it is also limited to modeling 5 core components. The other important thing when defining your MolFits file is making sure you have the right species tag or name, which should correspond to the name of the species within the spectroscopic data files. So you can cross-check this by running a function known as line identification, which looks through a range of user-specified frequencies to identify the different lines, from which you can confirm what the name of your file should be. Now, this also requires 2 more files, one of which is the observations XML, which gives you basic information about your observations, such as the frequencies covered, the background temperatures, the gas densities, dust information, and so on. And all of this is encompassed within a main input file, which also includes other parameters such as the number of iterations and the telescope size, for example. Taking a look at what the outputs of X-class are, here we have the example towards OH once again, towards the source W3OH. And here we have on the left the observed spectra in black overlaid with the fit in green. So each time X-class runs and you add a different component, it gives you this fit spectrum as well as the residual, so the chi-square minimization. Now, I would ignore this corner because this is X-class simply trying to fit this feature here, which is simply noise for us because that is not part of the relevant spectra that we're studying. So the main outputs are the fit parameters after each iteration, because you might keep adding components, the chi-square results for each iteration, and the best fit parameters once you're done. Now, these best fit parameters are what we translate into column densities because those are the values that we include as our input. Now, for species such as OH with hyperfine structure splitting, what X-class does is it weighs the contributions from each of the different hyperfine lines to model the total column densities. Now, the column densities wouldn't make sense without an error estimate, especially for absorption spectra, because the errors mainly arise from uncertainties in the continuum temperature. And for this, we use a Monte Carlo approach or a simulation of multiple probabilities. And we sample n spectra by generating each time the addition of pseudo-random noise to our observed spectrum. So in the first iteration, you would use your observed optical depth, which is proportional to the ratio between the main beam temperature and the continuum temperature. And in the second iteration, you would have a different tau, which is fit using a different ratio. Now, this ratio differs from the first because of the addition of this noise term, that is delta t, to both the numerator and denominator. Now, this is run each time, wherein which X-class uses the initial guess or the initial input mole fit file and produces the best fit parameters for each new spectrum. So you get n output files now. So here is an example for two of the OH components using 1,000 runs of X-class. So the different curves represent the different iterations, and the black solid line in both cases is the mean, which is the best fit for our observed spectrum, and the 5 and 95 percentile values are the 2 sigma levels of your errors. So from the spectra using X-class, we were able to obtain the column densities as well as estimate the errors. So to summarize, I'd just like to say that hopefully I was able to show you that the versatilities of using X-class for analyzing absorption line spectra using the function myXClassFit. You can also study maps using myXClass MapFit. Now, this is not restricted to absorption spectra. You can also use this for your SOFIA emission lines and or any other data that you have from any other telescope. But the HiCal team will provide column density profiles for each species and each of our targets. And you can also find the data from HiCal in the archives using this project ID, which you can then model yourself and cross-check the values. So that's a good case study. And with that, thank you.